think I'm going to get started. So, welcome everybody. Good afternoon. My name is Robert Thomas Kearns. I am the Restoration Partnerships Coordinator here at the Massachusetts Division of Ecological Restoration in the Department of Fish and Game at the Commonwealth of Massachusetts. And welcome to the Dam Buses webinar series, a collaboration between the Massachusetts Rivers Alliance, the Charles River Watershed Association, and the Massachusetts Division of Ecological Restoration. This webinar offers basic information about dam removal. It's not intended to advocate for the removal of any particular dam or dams. For the webinar series and topics and exact schedule, please visit our colleagues at the Mass Rivers Alliance website at www.massriversalliance.org. We are adding sessions to the series, so we recommend you check the site frequently to see the latest information. Also, please mark your calendars for the next two sessions, which will be February 4th and March 4th. February 4th webinar will be about the Dam Atlas 2.0 with Emily Vogler from University of Rhode Island. And the March 4th will be Dam Removal and Extreme Weather with Dr. Sarah Null of Utah State University. So put those on your calendar and make sure to sign up on the website. In today's webinar is about titled Restoring Aquatic Habitats Through Dam Removal. And a few housekeeping items. Number one, this session is scheduled to end around 1 p.m. Please put your questions in the Q&A function at the bottom of your screen, which we will be tracking. We'll hold them to the last half hour's question and answer sessions. Please put your name and affiliation in the chat. And also, please note the webinars are being recorded. Recording and any other materials will be made available on the Mass Rivers website. And also want to thank folks for completing the post-webinar surveys. And we will be having that at the conclusion of today's webinar as well. And I'm delighted to introduce our speaker today, Dr. Allison Roy, who was one of my former professors at the University of Massachusetts. Dr. Roy is a unit leader with the U.S. Geological Survey's Massachusetts Cooperative Fish and Wildlife Research Unit, an adjunct research professor in the Department of Environmental Conservation at the University of Massachusetts Amherst. Dr. Roy works closely with state and federal agencies to co-produce research and characterizes anthropogenic impacts on aquatic ecosystems and assesses responses to conservation and restoration. Her field-based research typically employs large spatial gradients to identify stressors and responses, species-habitat relationships between lakes and streams. Her graduate students and postdocs have worked on numerous projects in New England and have informed winter lake drawdown guidance, dam removal prioritization, water conservation, freshwater mussel restoration, and river herring management, among other topics. With that, I will let Dr. Roy share her screen and get started with the presentation. Very excited to have you.
Great. I'm excited to be here. How does that look?
Perfect. Looks great.
Okay, great. Thank you so much for the invitation to come here to Dam Busters. This is a wonderful series, and I love the goal of just trying to increase dam removal and learn more about how we can all do a better job doing that. And so I'm delighted to come and share a little bit about ecological responses to dam removal. Robert, I appreciate the introduction. I was going to mention that that our class back in 2017, 2018, so Robert was in my class that we led that was a dam removal practicum, and you were doing dam removal work then, and I'm so happy that you're continuing to do so much more dam removal work in the state. So thanks again. I wanted to first acknowledge two of my students who created a lot of the work that I'm going to be presenting today, including a lot of the slides. They're Kate Abbott, who received her PhD in 2023. And prior to that, Peter Zaydel did his master's looking at the effects of dams. So Kate worked on dam removal and Peter did the initial work of just the effects of dam. There are also many other co-authors in the work that we've published and some that still has not yet been published. This work was largely a collaboration with the Division of Ecological Restoration and Chris Houle, who was working there at the time. The initial funding came from the National Fish and Wildlife Foundation, but we had several other funding sources and collaborators throughout the time of our work that happened between 2015 and 2022. So I'm excited to share some of those results today. So let's jump right in. So as we know, dam building started kind of in earnest in the 1800s, heavily in the eastern United States, trying to create dams largely to power mills, like in Lowell, this picture up on the right. And then, of course, spread throughout the nation, resulting in fragmentation of our streams and rivers and creating this mosaic of unnatural aquatic habitats. So the Northeast is, of course, the initial trendsetter, and it even has maintained its position with the highest density of dams in the country. There are over 7,000 documented dams that are shown in the map here in New England, but as most of you know, that is not all of the dams that exist. It's largely an underestimate. We estimate over 14,000 dams in New England, which is pretty incredible. They have shaped our landscape entirely. Most of these dams are small dams. By small, I mean less than 15 meters. They're run of river. When I say run of river, I mean the water coming in is the water coming out. So they're typically unmanaged and unlikely to change the discharge, the total volume of water that comes through. But of course, they do change velocities, the creation of a dam in streams. Despite their small size, we know that they have large impacts, not just because there are a whole lot of them, although that's a big part of the story, but there are also impacts associated with each and every dam. Impacts include physical impacts. So putting a dam in can alter the channel form itself, the shape of the channel. It blocks sediment flow, and fine sediments are really important for aquatic habitats. Of course, the blocking of water alters velocity, creates slower velocities upstream of a dam, and can create pockets downstream. Chemically, dams can alter stream temperatures, and I'll talk more about that today. Trap contaminants, especially associated with those fine sediments that are trapped behind these dams, and alter nutrient dynamics. Again, what is kind of linked to the slowing of flow and the algae that kind of builds up oftentimes in impoundments. And then these physical and chemical effects affect the biota that live in the streams. The most obvious that people think of first is blocking fish migration, but there are so many more ecological ecosystem impacts that dams affect. And so they affect assemblages of fishes and macroinvertebrates, mussels. They affect riparian vegetation, and in a lot of different and variety of ways. So we do know a lot about the effects of dams, although understanding how they vary across the landscape is still kind of something that details that we were interested in working out with our research. But we were really interested in understanding what are the ecological responses following dam removal. So if these are the impacts of dams, what do we anticipate following dam removal? What might other people anticipate? And what are the best ways to document those ecological changes? And so these are the questions I'm hoping I'll be able to answer for you as part of this talk. Okay, so when thinking about monitoring effects and responses to dam removal, the first aspect I want to think about is the spatial aspect. And it's helpful to think of dams and the streams surrounding them in three separate sections, even though these sections are connected to each other, they're in this figure kind of separate. So the upstream section, which is upstream of the impoundment that is formed by the dam. So the impoundment is that area that's widened and slowed down because of the dam structure itself, which is a very unique habitat, different than the free-flowing habitat, both upstream and downstream. But the responses we expect to see are not just in the impoundment, but also downstream of the dam. And even in some cases, upstream, especially when we're talking about organisms that move throughout a stream system. Temporally, we need to think about the time scale of how these responses might come to play. So we do know that dam removal is a disturbance in itself. And so a disturbance suggests that that's going to cause some negative impacts. Those negative impacts could be on the order of hours. They can be on the order of days, years, and even decades. And so understanding what these short-term effects are and the longer-term effects are really important. Presumption is that it's going to get to a point where it reaches an equilibrium, and hopefully an equilibrium that is in better condition than prior to dam removal, but that really is likely to depend on the system, and then the rate of these temporal recoveries will also depend on the system itself. So here's a picture of a handful of dams in Massachusetts. Actually quite beautiful to a lot of people, and one of the interesting things associated with talking with the public about dams and dam removal. I put them here to show that there's a variety of dams on the landscape, and the variety is not just about the dam infrastructure itself, although that is really important, but also the setting that they're in. Dams are in urban areas and rural areas, in lots of different types of streams throughout our region. So of course, not all dams are created equal, and in a lot of different ways. So the infrastructure ways I'm thinking about are the height of the dam, the size of the impoundment that they create, and the shape of that impoundment, how long that water is slowed down to increase the hydraulic residence time in the impoundment. There's also differences in these streams and whether they're in high elevation areas, steep slopes, that sort of thing, and how big that watershed is that's draining to the dam, and the watershed itself and what other things are going on in the watershed, including the land cover in those watersheds. So we expect that all of these characteristics affect the response to dam removal. And so we took on a study where we compared a whole lot of dams over a period of time to quantify those ecological responses to dam removal, but also to try to understand how these sorts of variables can explain potential differences in ecological responses. So dividing this talk up into a few sections, the first is the effects of dams and dam removal on water quality. It's really important to talk about the effects of dams before talking about the effects of dam removal, so you have that in context. In terms of water quality, we focused on temperature and dissolved oxygen, but as I already mentioned, there's a suite of other water quality factors that are affected by dams. And then I'm going to talk about the responses of aquatic macroinvertebrates, which are typically used as indicators of water quality. And so they fit nicely into this story to understand these sorts of ecological shifts. And then finally, I'm going to take a little bit of the lessons we've learned and conversations with partners and others to use this to guide, provide some guidance to you about how to monitor for the ecology of the stream if you're interested in doing that with dam removal, and how to use this information for prioritization if that's of interest. So we'll jump right into the water quality piece. And I first want to introduce you to our study sites. Some of these you may be familiar with. We had 11 sites that had dam removals between 2015 and 2021. They represented a range in dam heights and drainage areas, a range in land cover. I posted the forest cover there. The goal was to, again, get a variety to understand how these factors might influence the response. You'll see that most of the dams are in the eastern part of the state. We tried to get, again, a variety, but some of the dams didn't quite get removed when we wanted them to. So we had 5 other dams that we sampled prior to removal, but that weren't removed in the time frame that was useful for us in our study. Some of you might know that some of these dams have recently been removed or will be removed very soon, which is super exciting. And I'm in discussions with DER to try to plan collection of post-removal data at these sites as well. So here we have all these stream sites, and we sampled them before removal and after removal. Ideally, we had multiple years before and after removal, but obviously those dams get removed in different timelines, and so some of them had not a whole lot of time before, and some of them had not a whole lot of years after at the time that we wrote this up. So when thinking about the water quality impacts, I think it's helpful to first talk about what happens when you put a dam on a stream. So you're blocking the flow and creating this, what we call impoundment behind the dam, that slows the water, that obviously increases the surface area of the water body. It decreases the velocities in that impounded area upstream of the dam, increases the amount of time the water is spending in that impounded area. And also, because of the widening, increases exposure to solar radiation. All of these things are expected to increase temperatures both within the impoundment, but also downstream, because again, these are run-of-river dams and most of them are spilling over the top. And so here's a quick diagram on the top that shows what we would expect the temperature to be farther upstream of the impoundment, within the impoundment, and then progressively downstream of the dam. And we expect that the temperature slowly decrease downstream of the dam. The dam would be spilling warm water, but then would decrease as more cold water inputs from groundwater come into the stream and mix and cool things down. For dissolved oxygen, since of course warmer water holds less oxygen, we would expect reduced dissolved oxygen in those areas in the areas that are warmed. We also would expect reduced DO because of the lack of turbulence in the impoundment. Although I'll also acknowledge that in impoundments, we can get buildup of plants and algae. And so there's a lot of photosynthesis, which can create large diel shifts in dissolved oxygen. So this is the sort of the expectation we are going in with. So to sample, we deployed loggers for both temperature and dissolved oxygen. The temperature loggers were deployed year-round and set to measure temperature every 15 minutes. We downloaded them and checked them and calibrated them twice a year. The loggers were placed upstream of the impoundment, as you see in these yellow X's in the diagram, within the impoundment, a single one there, and then a series of them downstream of the impoundment, again, to capture that distance downstream that we might see elevated temperatures and the footprint, the thermal footprint downstream of the dam. Dissolved oxygen was only sampled in 3 locations upstream within the impoundment and immediately downstream. And because these loggers are much more expensive than temperature loggers, we rotated the loggers throughout sites. And so they were deployed for a week at a time in the months of June, July, and August in each system. And we focused on those summer months because that's when we expected the impacts of dissolved oxygen to be the highest. They were also set to 15-minute intervals throughout that study period. Here's a couple of pictures. All of these loggers were placed within PVC pipes, and in the impoundment, they were floating with toilet bowl floats, creative use, and attached to rebar in other locations. Importantly, they were put in the areas where the water was spilling over the top in the impoundment or in flowing water areas in the stream sections. So let me jump right into results. First, about the effects of dams. So what I'm showing here is the downstream warming. This is the difference between the temperature downstream and the temperature upstream. So here we're thinking that the temperature upstream is really a reference or a control. And so anything downstream has been warmed from the impoundment. And that difference is showing the warming effect of the impoundment and the dam itself. So the first thing that should pop out is that there's quite a range. You've got our 11 sites across the bottom there. We had a range from some sites that even showed that downstream it was a little bit cooler than upstream, but most of the sites were warmer downstream, and this varied greatly across sites, with some of the highest temperatures being on average 4 degrees Celsius higher in the downstream sections than upstreams, which is a huge change in effect of the dams itself. So what explains this variation across sites? Well, we found that the bigger the impoundment, and specifically how much wider the impoundment was relative to the stream channel, the higher the downstream warming or the effect of that dam and impoundment. Also, if the temperatures upstream were colder, then we saw more of a warming effect. And that makes sense because, you're looking at the difference there. And so if it's colder upstream, then the dam itself can have more of an impact. Which was helpful to find. You can see that also in this next figure that I'm going to show, which is a little different. So the arrows here indicate the change from downstream to upstream. Again, each of the sites is across the x-axis. And so the longer the arrow, the more of the shift or difference between upstream and downstream in temperature. And so you can see that those that started lower at colder temperatures changed more, though that's where the longer arrows are, versus those that started already pretty warm. They didn't change quite as much. Now, what I wanted to point out here is how the meaningfulness of the actual temperature differences. So this has the temperature on the y-axis, and it's divided into warm water, cool water, and cold water. These are designations based on fish use of streams. And so you can see that we started with two of our streams upstream are cold water streams, but because of the dam, they created downstream environments that were shifted from cold water to cool water. We had several that were cool water streams that actually shifted to warm water streams simply because of the dam itself. And of course, this has really important consequences, not just for the fishes, but all the organisms that would be dependent on temperature and potential shifts in assemblages associated with that temperature. So what happened after dam removal? I'm going to start with a single site for the sake of simplicity. This is a site in Northampton, Massachusetts, Upper Roberts Meadow Dam. And what I have here is the date. So we had 3 years prior to removal and then 2 years post removal. And this is showing that downstream warming again, the difference between upstream and downstream. And so first you can see, one, that these are above zero in all cases. So in all cases, it is warmer downstream than upstream, but there's a clear shift between prior to dam removal and post dam removal. So less of an increase in temperature post dam removal in those first couple of years post dam removal. It shifted from being a cool water stream back to being a cold water stream downstream because of this dam removal, which I think is pretty awesome. The other thing I wanted to point out is this variability from year to year. So as you can see this, especially prior to dam removal, with 2016 having a lot more warming than 2015 and 2017. 2016 happened to be a drought year, a low flow year, and we tended to see across all sites that there were larger warming effects during lower flows and lower flow years. So what does this look like at all of the other sites? So Upper Roberts Meadow is that second to right one URM on this figure. And we've got before and after this downstream warming. So for a lot of these sites, you see a reduction from before to after in the downstream warming. But in some of the sites, you don't. Certainly that there's a wide variability across all of these sites and what those responses are. In terms of what affected those responses, not just that impoundment widening or the size of the impoundment, but also the height of the impoundment. So we found that if it was a taller dam, then we saw more of a change. And if it was a shorter or wider dam, that left a larger footprint after removal. And so we might have not seen as much of an initial response in temperature, but might see a longer term recovery in temperature. We also saw variability related to flow conditions. Again, you can see a few of these. So Old Rat and Sucker Brook all showed increases following dam removal. in terms of temperature. Those have some unique situations with wetlands upstream. And so again, the upstream to downstream comparison is a little bit odd. Sucker Brook in particular had only 1 year post removal, and that was a drought year. So that could have influenced that effect in that 1 year. And certainly other specific things in terms of flow and groundwater dynamics can affect each of these streams. So that's the end of the temperature story for now. I'm happy to talk more about that later. I'm going to shift to dissolved oxygen. So the dissolved oxygen story is actually pretty simple. So most of the impoundments had lower dissolved oxygen compared to upstream. So in this case, I'm not doing downstream to upstream, but I'm comparing impoundment to upstream. That's the difference. That's the variable on the y-axis. And you can see large variability. If they're below 0, that means that there's lower dissolved oxygen in the impoundment compared to upstream. So for the most part, they're lower. There's one site here that was higher dissolved oxygen in the impoundment compared to upstream. That's a wetland site as well. And these differences were explained again by the size of the impoundment or that impoundment widening. And in this case, cultivated land. So in sites that had higher cultivated land, we had a larger DO effect there. So we expect that nutrients associated with agriculture is leading to more algal growth and blooms and lower oxygen within these impoundments. So why and how much does this matter? Are these numbers meaningful? Well, it turns out that they are. And the way we looked at it to kind of discuss how meaningful they are was based on DEP's standards. So Massachusetts has surface water quality standards that have criteria for dissolved oxygen, and they say that certain class streams must maintain DO greater than or equal to 5 milligrams per liter. Class C streams must not have DO less than 5 milligrams per liter for more than 16 hours a day. And so we looked at that 16 hours a day. How many hours are they having oxygen below this 5 milligrams per liter? And that's what we show here. I'm showing the upstream impoundment and downstream. So those are the 3 colored bars at each of the sites. So of course, differences in those stream reaches, but 1, 2, 3, 4 sites have exceeded that threshold of over 16 hours a day, having really low dissolved oxygen. And any low dissolved oxygen can cause effects to biota. Certainly, long enough, we can have mass die-offs, we can have shifts in assemblages. Many organisms can't tolerate low dissolved oxygen. And a lot of water quality effects. So when you have really low oxygen, hypoxia and anoxia, that can trigger denitrification, mercury, methylization, those sorts of things. So real effects in the water quality system. And given that most of our impoundments had some period of time with that DO less than 5 milligrams per liter, this felt like a very important and meaningful effect of dams. Great news. You take out the dam, you can fix the DO problem. So, I mean, this couldn't have been clearer. You see before these yellow bars below the line, and then after, they're greatly reduced, maybe just slightly below the line or even above, having higher dissolved oxygen in the impoundment compared to upstream. We found that the most significant improvements happened at sites that had the lowest dissolved oxygen in the impoundment. So if it was the biggest effect of the dam, then you're going to see the biggest improvements, which makes sense. That said, that the potential for their restoration was constrained by the conditions of the watershed and in particular the stream upstream. Again, we did have some sites that had more slow water and wetland habitat upstream. And so when we're comparing the impounded area to that section, that we might not see differences or see, again, where you get more flowing water, you get higher dissolved oxygen. We think these quick recoveries were really because the water was flowing, the temperature effects happened right away. And in terms of downstream of the impoundment, we actually didn't even see that many effects of the dams itself because of turbulence. So really the problem with DO is within the impoundments, and it can be fixed with dam removal. So in some of this part, so we saw that dam removal can cool temperatures downstream, but it's certainly variable, and thinking about that restoration process is important, and thinking about that timeline. So how much widening there was, how open the canopy is certainly going to affect the timeline for overall recovery. So we saw great changes immediately, but not full recovery to upstream temperatures. Didn't talk a lot about other variables other than mean summer temperatures, but we could also see changes with dam removal on the frequency and duration of these thermal exceedances that are important for biota. From dissolved oxygen perspective, we saw that improvement within the next year following removal, but the magnitude did vary across sites depending on the magnitude of the impact pre-removal. So now I'm going to shift a little bit to the effects on aquatic macroinvertebrates, all at these same sites that I showed before. For those of you who aren't familiar, macroinvertebrates are commonly used throughout the country as indicators of water quality. Almost all states have used macroinvertebrates to monitor water quality, really because of the Clean Water Act requiring that surface waters have to maintain certain physical, chemical, and biological conditions. Massachusetts then adopts those things and figures out how to include those into their standards for aquatic life use designations. And so sampling the macroinvertebrates is a way to determine that, that we have good biological integrity in our streams, or to figure out where there is impairment. And the concept here is that with increases in stress, we see changes in biota from the more sensitive taxa to those that are more tolerant and lower diversity of taxa. So this biological condition gradient is kind of at the base of understanding biological integrity. And Massachusetts recently developed a simple index of biotic integrity to quickly measure from the macroinvertebrates what the quality of the streams is. So how are macroinvertebrates expected to be impacted by dams specifically? Well, first, through the variables that I just mentioned, dissolved oxygen and temperature. Those are both important for macroinvertebrates, as are physical habitat. Things like sand and gravel is going to affect organisms. These are benthic organisms, mostly on the bottoms of the streams, and so they're affected by this habitat. The hydrology, flow rates, velocities will also affect what macroinvertebrates can be in there, and the nutrients and algae. And it's a whole long lecture in itself to talk about how these stressors affect macroinvertebrates, but suffice to say that they can affect them sublethally through altering their metabolism and activity levels. Interestingly, so a lot of these aquatic macroinvertebrates have adult life stages that are terrestrial, and so the temperatures can affect the timing of the emergence, even when temperature shifts are really small, like a couple of degrees Celsius. Changes in the timing of emergence, which can have phenological effects. And then, of course, shifts in species composition based on the tolerance of the organisms to each of these different factors. So we sampled macroinvertebrates in both the flowing stream reaches and in the impoundment, and we had to sample them differently depending on what sections they were in. In the flowing reaches, we used something called a Cerber sampler, which is simply a square. That's what's pictured here, where you rub the rocks in that square and you collect all of the macroinvertebrates floating into the net behind it. That really captures a quantitative area to get a good estimate of the density of the macroinvertebrates in the streams, but it's really focused in riffle habitat or heavy flowing water habitat. So we also did multi-habitat sweeps that could get edge habitat and pool habitat and other habitats within the stream reach and capture the full diversity. In the impoundments, we took a similar strategy in using a ponar grab to get a very fixed area section. So that's just a thing that we dropped off of the canoe and raised up, and it grabbed a slug of the bottom sediment and sorted through that for the macroinvertebrates, and also sweeped within the vegetation along the edge of the impoundments. So here's what we found. First, the effects of dams. variable I've pulled up here is cold water taxa, since we just got finished talking about temperature. So we have upstream and downstream, and in many of the sites we saw fewer cold water, a lower proportion of cold water taxa downstream compared to upstream at our site. So something that would be expected based on the temperature responses, although certainly we didn't see it at all of the sites, but we're seeing it at these sites that had the highest number and proportion of cold water taxa in them that had drastic reductions downstream of the dam. This is maybe a little bit more complicated way to think about macroinvertebrates, but it doesn't simplify it down just to a couple of taxa. So this is an ordination that includes all of the species and genera that we found and the abundances of all of them. And each dot represents a different sample. So I've got samples upstream, impoundment, and downstream reaches on different summers and dates and at the different sites. And so that's why we get as many points as we do. So the colors represent those different reaches, and if they're overlapping, they're very similar in composition, and if they're not, they're more dissimilar. And so I think pretty quickly you can see that the impoundments, the orange, is really different from the upstream and downstream, the flowing water. Not rocket science here, but macroinvertebrates are reflective of whether they're flowing water habitat or not. So lakes, macroinvertebrates in lakes are different than macroinvertebrates in streams. And even though these are all streams, the stopping and the slowing of the flow has created a completely different macroinvertebrate assemblage in those impoundments compared to upstream and downstream. A little less obvious is maybe the difference between the upstream and downstream, but you can see that the downstream, the green, are sort of shifting away from the upstream and closer to the impoundment. And I think that's largely reflective of the effect of that impoundment on downstream. Now I'm going to show you what it looks like after dam removal. Pretty amazing. They're all the same, right? So you remove a dam and you can get completely similar macroinvertebrate assemblages upstream in the impoundment and downstream, which is pretty remarkable and obvious. And this was happening really quickly after dam removal, which was actually quite a surprise. A lot of literature talks about the negative effects, initial perturbation associated with dam removal, and I'm not saying that isn't there, but it seems that when we're sampling them a year later, 2 years later, 3 years later, they're already recovering to a large extent. To try to convince you a little bit more of that, I'm going to go back to our site that I showed you earlier, Upper Roberts Meadow. And here it's just the upstream impoundment and downstream sections. And then I have yellow as before, then 1 year after, then 2 years after. So if you focus on the yellow first, you can see that the impoundment was completely different than upstream, and the downstream was sort of in the middle of those two. But 1 year and 2 years after, we saw the percent sensitive taxa fully recovered to what that upstream was. And this is a site where the sediment was allowed to passively release, which is a goal, as long as sediment isn't contaminated, of dam removal, is to let sediment go if possible, if it's not going to be harmful downstream. And here's an example where it really isn't harmful to the aquatic macroinvertebrates, which is cool to see. So to summarize all of this, our overall kind of picture here is that there's a lot of variability in what you would expect to dam removal, although the directionality of effect is largely similar across sites. The impacts of dams and the response to dam removals do differ among the sites, and I talked about how that differs based on the characteristics heavily of the impoundment and sometimes of the setting that it's in. Depending on what taxa you look at, they respond differently to removal. So I showed that with sensitive taxa and cold water taxa, and that these impoundments and downstream reaches can respond differently, both in terms of water quality and the macroinvertebrates. I will give a quick teaser to say we also saw this variability with fishes. So at all of these sites, we also sampled fishes, and I'm going to come back to this webinar series in a few months to talk about effects of dam removal on mussels and fishes. And so I hope you come back and check that out. In terms of recovery timeline, we saw that temperature recovered quickly, although not completely. So there is going to be some sort of delayed recovery, and we're really interested in how long it takes to fully recover temperature. Dissolved oxygen improved within a year And those macroinvertebrate metrics really showed that resilience within 1 to 3 years following dam removal. So hopefully, seeing this across 11 different sites can help give a guide to what you might expect to see if you were to do dam removal at another site, how your site might compare to some of these other sites, can help you determine whether you might be on one end of the spectrum or the other, and certainly what it looks like beforehand can help you determine what the potential improvement could be with dam removal. To be more specific about that, and if you're really thinking about how do and what do I monitor if I'm doing and planning for a dam removal, and how might this be used to help guide prioritization, I have a few more slides. So first, if you're focused on monitoring and you want to monitor water quality, or at least temperature and dissolved oxygen, although I think these lessons can apply to some other water quality variables as well. In terms of timing, so this before after is really, really powerful. A lot of times we don't have time and we don't have the data beforehand, but in truth, it takes a long time to get these dams out, right? So we should have time to go and actually monitor beforehand. Certainly, even if you can't get the before and after, having multiple years is really important. And I hope I convinced you with showing some of those sites and multiple years, and how drought years can really affect the response that you have. In terms of time of year, I focused on summers, but I think you could focus on any time of year when the impacts are the greatest if you want to understand what the potential impact could be. And so the impacts are greatest largely in the summertime, but also in the wintertime. The shoulder seasons are less so, where we would see impacts of this, and of course, this is just in terms of temperature. So it depends on the variable that you're talking about. But in our case, we focused the dissolved oxygen in the summer, and I think that was a reasonable thing to do given when the impacts would happen. And I think it's been very helpful to have continuous data, especially because storms can really affect things. And we did see, I didn't show this figure down before, but we did see that depending on the discharge, you can see different effects. So a lot more effects in low discharge than in medium and high discharge years and sites. In terms of location, you could see that thinking about these 3 separate sections are really helpful. I didn't show anything about that downstream temperature and footprint, but that can help you, especially when there aren't other impoundments and tributaries downstream, to see how far that effect can happen. And then within the reach, we focused on the water that's coming out, the spilling from the impoundment, and then sampling in areas that are well mixed. I think this is really important. If you were to put your temperature probe in a cold water patch, then you're unlikely to see the effects of the dam as much as if you were in a well mixed area of the stream. In terms of macroinvertebrates, timing, same thing, like multiple years is really important. We do see a lot of variability from year to year. And so to capture that variability and understand what the effect could be, having multiple years is important. In terms of time of year, my recommendation is really around what Mass DEP does. So they sample from July to September. That's their index period. And so collecting samples in the same way and in the same season as DEP helps to have comparison. So once a year usually works well when you're trying to just use macroinvertebrates as an indicator of water quality. And then in the different sections, and I thought it was really valuable for us to sample not just in riffle habitats, which again is what DEP does with their sampling, but in multi-habitats to really capture the diversity of the biota, and especially given all of the habitat changes with dam removal. So what's the estimate? Over 3,000 dams in Massachusetts, over 14,000 in New England. It's a big task. I know many people are thinking about where to put our efforts. Our approach typically is where people are willing to do it and where they're motivated people. And this is the low-hanging fruit strategy, which I do not disagree with at any bit. But the result is that there's a lot of variation in time and cost of dam removals using this approach. And I think collectively, there's a goal of increasing removal rate. But given that there are limited resources, we can't do everything everywhere. Thinking about where we can spend money for the most benefit, I think is a worthwhile cause. And so how can we use this information and restoration potential to decide where to remove dams? Well, the Division of Ecological Restoration has this restoration potential tool, which you should check out if you haven't before. So this ranks every dam. It gives it a score, a percentile score, with the red being more problematic or better to remove them because that they are highly valuable streams, have important species in them, offer a lot of increasing connectivity, and aren't in areas that are otherwise impacted by impervious and water withdrawals and that sort of thing. So how can we use the information from our research to kind of expand on this or to further understand the restoration potential? So I think there are a few things that we can do. One, the water quality data really lends itself well to a rapid assessment. And so as long as you can take them in close succession, fully understanding that temperatures change throughout the day, you could do just a spot measurement upstream and downstream, or upstream within the impoundment and downstream, and see what those differences are in terms of basic water chemistry characteristics. You could also do short-term deployments when there aren't high discharges and in the period of time when there's the most impact, to see whether and how much of an impact that would be. And you could use that to determine whether this is a high priority dam and whether the dam removal would affect these water quality parameters, how and to what extent. We had some sites that were upstream and downstream of each other, and certainly the reality of our landscape is that there are a lot of dams in succession, and we don't think a lot about those cumulative effects of dams, but thinking about them in sequence and the potential for the recovery based on them being in sequence is really important. We definitely saw that there was less recovery when we had a series of dams and they weren't all being removed. Also, I think it's valuable to think about how dam removal can be used for climate resiliency. Northeast doesn't only have the most dams, but it also has the most warming, lucky us. And so, there's a real opportunity here to think about dam removal as a way to reduce the impacts of this climate warming on our streams and rivers. Kate did a survey as part of her dissertation to ask how practitioners are using climate change, or if they're using climate change in dam removal decisions. And it's great to know that half were using them often or always, but there's also a large chunk that aren't using climate change in making decisions. And it's a real opportunity to think about where we can remove dams to improve access to climate refugia for biota, to connect habitats, to reduce flood risks, and to overall reduce the temperatures associated with warming climates. And my last point is that dams aren't the only thing out there in our watersheds. And I know we all know that, but in a dam removal session, I think it's really important to remind ourselves and acknowledge that it's only one piece of the puzzle. And that's how we should think about dam removals. It should really be part of a more holistic plan for watershed restoration if we really want to give our watersheds the best chance. So with that, I'm going to end. I'll let you know that all of the publications, there are several reports, dissertations, theses, and journal articles from the work that I shared today are on a slide that will be posted online. And if you have trouble accessing any of those resources, I'm happy to email them directly. And if I'm not able to get to your question now, I'm happy to answer them offline too. So thank you so much for your attention.
Awesome. Thank you, Dr. Roy. Great presentation. Our questions are coming in. And we got a lot of praise as well, and thanks in the chat. The first question, I think you answered this, but were any of the dams evaluated run-of-river dams? I think they all were, right?
Yes, they're all run-of-river. None of them had water withdrawals in them or were managed that way. I shouldn't say none of them have water withdrawals in them, because sometimes we do have dams that had to deal with, it was being used for backup for fire or something like that. But yes, they were all run-of-river dams.
Great. Next question is from Heather. She says, you mentioned that the low wide dam showed the most metrics variation after removal. Did that shape or type of dam play into a part in that?
The the the
The
lower, say
low
that again,
wide dams.
low wide. Yes.
Yeah.
And the question, say that again, is what is
Did,
the
did the
question?
shape or type of dam also play a part in that?
Yeah, so I mean we spent a lot of time thinking about how to quantify the impoundment. We did it in terms of volume, we did it in terms of area, but this width one was stronger than others in the predictive models. And I think it's because it also encompasses what's coming into that. So if it's coming from a multi-network, multi-channel, wetland-heavy area, that widening isn't as much. And also, like sometimes we get these long, narrow impoundments, and we had sites like that versus those that spread a lot wider and bigger. And I think it does make sense in terms of solar exposure, why that is more of a factor for both the temperature and the dissolved oxygen. We thought things like dam height, I guess we did get dam height in there a little bit to matter, but um, how leaky these dams are, I don't know. There's probably a lot of things about the dams themselves. Of course, with only 11 sites, you can't put all of these variables into our models, and some are related to each other. But we generally came up with this sort of schema that was more about, hey, the low wide are different than the narrow steep, and it's also different in where those are in the landscape. So those high ones are really in higher slope areas, often more cold water streams. So you can quickly see how these things can be confounded, right? Um, and so we see more of a change from upstream to downstream, which when they're lower, shallower, wider, these are often in low slope areas, closer to the coast, that sort of thing. And not seeing that change as much, but also not seeing the recovery as fast. And I think that's really true, given how wide and big they are. That makes sense. It'll be interesting to go back and look at these, 10 years later and after a canopy has come in to see
Yeah.
if they can fully recover.
I was wondering that too, thinking about canopy. Um,
Yeah, one thought to add to that is that, a lot of times initially following dam removal, that the canopy is created just from um, brush and low ground vegetation, that shrubs that come in right next to the channel, but it's not getting the big overstory canopy for years. So it's interesting. It'll be interesting to see whether that like short, yeah, what time scale it follows, right? More of that, the
when the
close canopy
trees are,
versus the overall tree canopy. Yeah.
yeah. Okay, Olivia asks, is there a concern that some of the macroinvertebrate species that thrive in the impoundment areas would suffer from dam removal and would this have negative effects on the ecology, or do they have sufficient habitat elsewhere?
You answered your own question in the question, so thank you for that. Yeah, like those that do really well in pond habitats, and when you make it a stream again, they're not going to do well. So, there's a suite of dragonflies, some of which are endangered, right? That need this slow water habitat. But the habitat that's creating from these dams is not natural habitat. There's lots of that habitat on the landscape, lots of lakes and ponds and wetlands that are really better habitat for this group of organisms. So it's a shift, but it's not a shift that's of concern to us. The other groups of taxa, so a lot of midges are found in impoundments, and usually that's a concern for people. So, we're seeing a loss of these more tolerant taxa to be replaced by those flowing water taxa that you would expect to be there naturally.
Great. Next question was, are the slides uh, the best for reference of presentation recommendations, or are they published elsewhere? Would love reference these as prioritization for the removal work in the Narragansett Bay. I think the slides will be posted after this, right? Is there anything
The
you want to add
slides
to
will
that?
be posted. Those sorts of ideas are really kind of coming from a kind of a broader knowledge, so it's not really in the publications that we have. But I'm happy to talk about those ideas and think about how this information can be used to guide and inform those decisions.
Great. For the water quality loggers, did I correctly hear that you recommend placing impoundment loggers near the dam in order to capture maximal flow of the impoundment? What's the question?
Yeah, so our thought process there was we wanted the flow or the water that reflects what's ending up downstream. And so sampling the water near the surface is not only the warmest because it's near the surface, you might get colder downstream, but that is the water that is spilling to downstream. And so that was our thought process in thinking about what to measure. If you were trying to get an overall average or the full variation, then it would obviously take a lot more loggers in there. But in terms of the simplest kind of approach, that seemed to make a lot of sense.
Great. Okay, Chad. Okay, great data. We're monitoring pre and post removal of all the numerous smaller dams could be cost prohibitive or disproportionate to the other project costs. Does this information allow you to define parameters where monitoring should not be necessary or required by permit supporting a permit by notification process if we can get there?
Yeah, I think that's a great question. It's like, do we need to be doing this everywhere? And, while the ecologist in me wants to say yes, I think we can learn a lot from this, learn what you might expect at these sites. I think the places that you want to be monitoring are where, as you point out, where there's a permit situation. So we're talking about taxa or water quality parameter that is really critical for standards. You might want to be monitoring where there's a large public investment and there's to try to communicate these sorts of changes. We might want to be strategic in what's monitored based on what parameters are having most affected by the dam itself. So to highlight some of these things, strategic also based on cost and the expertise and that sort of thing. So I don't necessarily think that we should monitor all dams and everywhere in all places and at north that we can. But that said, you mentioned like it's cost prohibitive. Dam removal is quite expensive, and the monitoring of this is actually a very, very small fraction. And so I'm a believer that if we could just set a little bit of funds aside associated with dam removal to understand those changes, then we can learn a lot, continue to learn as we continue to do more dam removals, and then also really just document the benefits of dam removal, which is really going to help that continued removal.
Awesome, thank you. We have a couple, running out of time, we have a couple interesting questions, quick ones. Jessica asks, on average, how far upstream from the impoundment did you place your upstream loggers?
Yeah, so the trick is figuring out where the impoundment ends, especially for those long linear impoundments. So we tried to make sure that there was flowing, and because we're coupling this with the macroinvertebrate sampling too, like to have a riffle or something like that in the upstream. Usually, though, it was determined based on access. So we weren't trying to go too far upstream, but just get above where the impoundment was created, meaning the slower water conditions.
Great. Thank you. The last question was from Molly. Did any of the dam removal projects you studied I'll say this again. Did any of the dam removal projects you studied have plant vegetation that would create canopy, i.e. trees, in the former impoundment?
I think a couple of those sites did, and they were strategic for different reasons. In our time frame, first we didn't measure the riparian canopy, although we did do a stream habitat assessment. So I've got some information about that, but we didn't, kind of look at that extensively. And we were doing this in a pretty short time afterwards. And so even in sites where there were plantings, it wasn't a time frame that we could see that. Again, this is much more interesting for a longer term look back, which is something that I'm working with the Division of Ecological Restoration to consider at these sites now that we're about 10 years post removal. So it's really exciting to look back at these sites and see where we are now.
Awesome. Well, we're right at 1 o'clock. So I think we're going to wrap it up. We do have one more question, but I think we can do that after. Is that okay, Allison?
Sure thing.
Okay. So I'll send that to you from Newsrot. But yeah, thank you, Dr. Roy, for this great presentation. Everybody for coming to this great Dan Busters presentation. We had over 80 people. I was watching it tick up, and yeah, just want to remind folks to make sure to follow Dan Busters for the next ones in the coming months, and also stay tuned on the website, and also like we said, the slides will be posted soon, hopefully, in the recording. So we're very excited. And with that, have a great day, everybody.